the remainder of this course will concern antiderivatives and the indefinite integral, and a couple things next week which are related. Now, with the derivative, we started with a function and produced another function called the derivative. An antiderivative, we're doing the same type of thing. We're starting with a function, we want a new function. But in this case, the antiderivative, instead of going from function to derivative, wants us to go from derivative to original function. Definition: an antiderivative of f is a function whose derivative is f. I should say is a function capital F whose derivative is f. So because we are going to use in this example capital F. So an antiderivative of lowercase f is a function capital F whose derivative is f. All of the f's might be a little confusing, but it is, I think, and all the textbooks think, the best notation for this. Because it gives a relation, well, we'll see. Example, find 3 antiderivatives of lowercase f is 5x to the fourth. So here, we're looking for a function whose derivative is 5x to the fourth. Well, we've seen that. We've seen 5x to the fourth before, I think. Here's one. If you let f of x equal x to the fifth, the derivative of capital F is 5x to the fourth. F, capital F, is an antiderivative of lowercase f because the derivative of capital F is lowercase f. Well, okay. There's a third of the credit. What else can we do? Well, what if we take x to the sixth? Well, that's not going to work. What if we take e to the x pi x? Not going to work. What if we take x to the fifth plus 1? That derivative, the derivative of that, is also 5x to the fourth. What if we take, I don't know, let's see, we have x to the fifth plus 1. What if we take x to the fifth minus pi? Well, the derivative of that is also 5x to the fourth. So we found 3 different functions, whose derivatives are 5x to the fourth, each one. Well, this example suggests something. The only way, I mean, if we did something else with the x's other than x to the fifth, we wouldn't be able to get a 5x to the fourth. The only way we could have adjusted that was by throwing an additional constant on there. And that holds in general. So theorem, general form of the antiderivative. Let capital F be any antiderivative of lowercase f. Any other antiderivative is of the form capital F plus c for some constant c. The only way we can get another antiderivative is by changing the constant around. And that's an important thing to find, especially since we know all these derivatives. So we're going to call this a definition. And this definition may, well, the notation for this definition may not seem clear now, but by the beginning of next week it will. Definition, let f be a function. The indefinite integral of f, indefinite integral, I-N-D-E-F-I-N-I-T-E, integral, I-N-T-E-G-R-A-L, of f, maybe I should say f of x, denoted, this tall squiggly thing, f of x, lowercase dx, gee, where have we seen dx before, is the most general antiderivative. That is integral, the indefinite integral of f of x with respect to x is capital F of x plus c, where capital F is an antiderivative and c is a constant. So let's do a couple examples of this. Example. We'll do 2 examples. Integral of 5x to the fourth with respect to x. Well, we want the most general antiderivative. Well, x to the fifth is an antiderivative. So the most general antiderivative So the most general antiderivative is x to the fifth plus c. And you don't have to say where c is constant or for some constant. That's standard enough that that's true, or that you can just say plus c. This example should have directions. Evaluate each indefinite Ind integral int. Well, there's one. What about cosine of x dx? Well, for the first one, we needed a function whose derivative was 5x to the fourth. For this one, we need a function whose derivative is cosine. The derivative of sine is cosine. Now, these indefinite integrals give antiderivatives. We have some nice formulas for derivatives. So you might expect there are also some nice formulas for antiderivatives. And there are. So let's look at table of indefinite integrals. This is posted on Canvas. It just says indefinite integrals. There are fewer of these than there are derivative rules. So first, integral of a constant. Indefinite integral of a constant is constant times x plus c. The derivative of kx, remember, k is a constant, is k. So the most general antiderivative is kx plus constant c. Next, the power rule. X to the n. So for x to the n with derivatives, we brought the exponent down and subtracted 1. So we multiplied, subtracted 1. Well, here we're going to do that in the opposite form. Given an x to the n, we're going to divide after adding 1. So add 1 to the exponent and divide. So if you had integral of x squared, it'd be 1/3 x cubed plus c. Derivative of 1/3 x cubed is x squared because the 3's cancel. Now notice that one says it doesn't apply if n equals -1. If n equals -1, rule 2 doesn't work. But rule 3 does. It's a very convenient result. Let's just say convenient. That's a good enough word for it. I mean, it's really kind of amazing that this rule works all the time, except when you get a 0 in that denominator. And when that happens, you have a very nice logarithm result. 1 over x, derivative is logarithm of the absolute value of x. The absolute value of x is because 1 over x can have negative input. So we just throw the absolute value on there to make up for that. Well, to take care of that, I should say. Next, e to the x, derivative of e to the x is itself. And notice in all of these, you can check your work by taking the derivative on the right side and checking that you get the integrand, which is the thing inside the integral. Derivative or antiderivative of e to the x is itself, and all of these, of course, have the constant of integration. It's the most general antiderivative. And now we have some trig ones. Integral cosine is sine. I wrote it in this order because the derivative of sine is cosine. So these actually parallel the derivative results quite nicely. Derivative of sine is cosine, so the antiderivative of cosine is sine. Derivative of cosine is negative sine. So the antiderivative of sine is negative cosine. And I should be saying an antiderivative. Is an antiderivative of sine x, negative cosine of x. And of course, plus c. Now notice here, we don't have the next one saying an indefinite integral of tangent of x. To do the indefinite integral of tangent of x, you need Calc 2. However, we have actually seen it. In week 2 we saw it somewhere. We took a derivative and wound up with tangent of x log absolute value of cosine x. No. Negative log absolute value of cosine. Well, we didn't have absolute value. But here, the tangent rule says, since the derivative of tangent is secant squared, the indefinite integral of secant squared is tangent x plus c. Indefinite integral and antiderivative are not the same. I mean, I sometimes use them interchangeably, and that's incorrect. The antiderivative and antiderivative is just one of these things without the c. The indefinite integral gives all of them, meaning the 1 plus c, the most general. Now on this, there are 3 other ones. You can ignore the writing over there. That's an example I'm not going to cover or ask. But these other three go with the other three trig functions. Derivative of cosecant is negative cosecant cotangent, so integral of cosecant cotangent is negative cosecant plus c. Secant tangent is the derivative of secant, and cosecant, negative cosecant squared is the derivative of cotangent. On the bottom you have three inverse trig. I will not ask those, but next week I will mention a little bit about them. They will not be on any test or the final, so you know. I just didn't want to rewrite that page and scan it. It's easier to just say, ignore those last three. Now, the derivative had convenient properties that we use to evaluate derivatives. The antiderivative, or the indefinite integral, also has convenient properties, fewer convenient properties. Notice in that there was nothing with products, nothing with quotients. You can't do, there is no product rule or quotient rule for doing these integrals. But a very convenient result is the sum and difference rule still applies. So here, properties of the indefinite integral. Let f and g be antiderivatives of f and g. Let k be a constant. Integral of f plus or minus g is integral of f plus or minus integral of g, and then plus a constant. Now, you might think, well, if we do these one at a time, we get a constant from this and a constant from this. But you can just smash them together as one constant at the end. And who wants constants all over the place? We just need one. 2 plus 4 is still a constant. So when you have two things added together, you can do them one at a time, just like with derivatives. And another very convenient result is if you have a constant times your function, you can pull that constant outside of the integral, and then take the integral, and you get a constant rule. Just like with derivatives, you can pull constant out. Just like with limits, you can pull constants out. And notice in all of them we have a plus c at the end. We need that because the indefinite integral gives the most general antiderivative. So let's just do these three for now. Evaluate each indefinite integral. Maybe I should throw a negative on one of these. Let's throw a negative on this e to the x. Sorry if you already wrote that. Fine, let's leave it as a positive. Let's put a negative on this one. There. So what do we have for this first one? Well, we have three things added together. We can do them one at a time. And I'm not going to write that. I mean, I could write it as integral 4x cubed dx plus integral e to the x dx plus the other one. That's a lot of writing. I mean, we've been doing things one at a time with derivatives, so I mean, we're used to doing, and limits, so we're used to doing things one piece at a time. So let's first look at this 4x cubed. What can we take the derivative of to get 4x cubed? Well, the answer is x to the fourth. But which rule applies to that? Rule 2 applies to that. The, what's it called? Power rule. How does the power rule work on that? Well, first I'm going to use that constant rule to get rid of that 4. Who wants an extra 4? And we just have x cubed. Apply rule 2, n equals 3. So you get 4 times 1 over 3 plus 1, x to the 3 plus 1. And 4 1/4 cancel. And with this, what I just wrote on the side, and I threw a plus c there just so it was completely correct. I don't want any of you taking a screenshot of that without the c and then saying I don't know what I'm doing. If you want to say I don't know what I'm doing, I'm sure there was something this semester that I did that could allow you to conclude that. Or maybe not. Pretty careful. Where were we? So we have x to the fourth for that. We did a plus c over here, but with all these, I'm just going to do one constant at the end. Plus, that's a plus sign. E to the x, well, we can do that with rule, I believe it was rule 4. e to the x is the derivative of e to the x. So e to the x is an antiderivative of e to the x. How about this last thing? Well, we have 5x to the negative 4. Let's pull that 5 out. Who wants a 5 there? Again, with negative exponents, you have to be careful. So negative 4 applies with rule 2. This x to the negative 4 applies to rule 2. Rule 2 applies to x to the negative 4. So what do you get? Negative 4 plus 1. Over negative 4 plus 1. What's negative 4 plus 1? Negative 3. So we get negative 3 there, negative 3 there. So what do we have? Negative 5/3 x to the negative 3. And then we'll throw our constant on that. And when doing these, the nice thing, if you know your derivatives, is you can check your work. Just go backwards. Take the derivative of this. 4x cubed plus e to the x minus 5/3 times negative 3 becomes a positive 5. X to the negative 4. So that's right. How about this one? Well, go through each piece and do a power rule. Does that work? Well, usually when you're asked if something works in this context, it doesn't. You can't just go through each piece like this. This isn't a sum. It's a quotient. You have to do something with this before you can just go through each piece. So if you wrote this, put a large x through it. If you didn't, because you were looking and thinking, what is he doing? Don't put a large x through it. I mean, I guess you could. I'm not going to stop you. But what we can do is reduce this fraction. How do we reduce it? Well, x squared over x is x. Negative 2 over x is negative 2 over x. Root x over x. I know we're going to eventually have to use the power rule, so instead of writing that as 1 over root x, I'm just going to write it as x to the negative half. It's easier to use power rule when it looks like that. Well, now we just have, for the first thing, a power rule. X to the 1. 1 plus 1 is 2. Use the power rule. The next one, well, first, just write the negative 2. Because there's a negative 2 there. When you take the negative 2 away, you'd have 1 over x. How do we take an antiderivative of 1 over x? Well, rule 3 took care of 1 over x. Log absolute value of x. So if we throw a negative 2 on everything, we get negative 2 logs of the absolute value of x. And how about this last piece, x to the negative half? Well, negative half is a number. We use the power rule. What's 1 minus a half? One minus a half is a half. What's 1 divided by a half? 1 divided by a half is 2. So all this work, and we're left with a 2x to the 1 half. You could write that as root x if you want. And then we need a plus c. So we had 2 power rules in there and a logarithm, but we had to split the fraction. You can't just jump into fractions. You have to use the rules we have. And how about this last one, tangent cosine? Well, I already told you can't do tangent, but you can't even split this into integral tangent times integral cosine. What can you do with this? We actually haven't done much, if anything, like this entire semester. if you have trig functions and none of the rules are going to apply, I would guess it simplifies in a convenient way. And this one does. How? Well, let's write it as sines and cosines, in terms of sines and cosines. Well, look at that. Cosine and cosine cancel. And we're left with sine. Rule 1, 2, 3, 4, 6 says integral of sine, negative cosine plus c, because the derivative of cosine is negative sine. So maybe I should have also checked the work in this second one. Derivative here, x. 1/2 times 2x to the 1, just x. Derivative here, negative 2 over x. Derivative here, 2 and a half cancel. Half minus 1 is a half, so you get x to the negative half. And then derivative of the constant is 0. So try these computations. We'll be, next week, we will be doing lots of computations like these. So definitely try to get used to the indefinite integrals in the chart and these properties.